As a follow-up from the previous situation where I looked at a fixed inclined plane, I'm now going to let the plane do what it wants to. I'm going to make it rest on a smooth horizontal surface. The inclined plane itself is smooth, and there is a particle of mass small m moving along the plane, right? I'm going to have a detailed digression of this, and we'll look at it in very many ways. All right. So first things first. There's a particle of mass m resting on the inclined plane. What are the forces acting on it? There is mg, Mother Earth, and there is normal reaction from the inclined plane perpendicular to the plane, right? These are the two forces acting on small m. That far and no further. I'm assuming that this surface is smooth. Of course, if required, we could resolve mg perpendicular to the plane as mg cos theta and parallel to the plane as mg sin theta. But that's it. I mean, we could resolve it in other ways too. But this is one of the ways we could resolve mg. We could, if we want to deal with two standard directions, parallel to the plane and perpendicular to the plane, this is one thing that we could have done. Now, look at the inclined plane side of the story. What are the forces acting on the inclined plane? This is the inclined plane. There is capital mg acting downwards. There is normal reaction from the ground acting upwards, right? And if the inclined plane exerts on small m, n like this, small m will exert on the inclined plane a normal reaction n like this, right? Which could be resolved as n cos theta downwards and n sin theta leftwards. Yes or no? Then from the ground, there is a normal reaction acting on the inclined plane, preventing the inclined plane from having a vertical acceleration. So essentially then what happens from the inclined plane perspective is that mg and n cos theta balance r. Mg and n cos theta balance r. R is a self-adjusting force. It manipulates itself in a manner that there is no net acceleration of the inclined plane in the vertical direction, right? That's as far as this is concerned. But what about n sin theta? Now, there is nothing to counter n sin theta. There is no friction. Everything is smooth. And there are no other forces acting. So, n sin theta stays put as an unbalanced entity on the inclined plane. Capital M, right? This is capital M. So, n sin theta produces on capital M a leftward acceleration, capital A. A leftward acceleration, capital A, right? So, the inclined plane has a leftward acceleration, capital A, owing to the influence of this n sin theta. Yes or no? I hope all of you are in tune with me and are in sync with whatever I'm saying, right? Now, if you are an observer sitting on the inclined plane, what would you observe about this particle? You would observe that the particle is sliding along the plane. That means, if you observe that the particle is sliding along the plane, what would you want to conclude? You would want to conclude that the relative velocity of small m, with respect to capital M is parallel to the plane. The relative acceleration of small m with respect to capital M is parallel to the plane. There is no relative motion in this direction. Along the common normal, if there was relative acceleration or relative motion of any kind, then it would result in loss of contact. There is no loss of contact. So, relative acceleration perpendicular to the plane is 0. But there is non-zero relative acceleration down the plane. An observer on the plane would not find this particle to have an acceleration perpendicular to the plane, but would observe an acceleration small a parallel to the plane. So this is the relative acceleration of small m with respect to the inclined plane, and this relative acceleration, at least we know its direction, it's parallel to the plane. And the fact that there is no relative acceleration perpendicular to the plane between the inclined plane and this mass m is because of a wedge constraint. That's the condition for it to maintain contact. So no relative acceleration in this direction. So whatever the inclined plane has an acceleration in this direction is also the acceleration of small m in this direction, so that the relative acceleration condition equal to 0 is preserved. So on small m, this is small m, What are the two things that you're going to see on small m? One, there is relative acceleration like this, right? That is a that is a inclined plane observer's perspective, this A. This is not, however, the acceleration of small m in the ground frame. No, this is not the observation made by a ground observer. What is this? This is the observation made by the inclined plane. The inclined plane reports, the inclined plane observer reports that small m has an acceleration like this. Yes or no, right? So this is only relative to the inclined plane. But what about the inclined plane itself? Is it fixed? No, it has an acceleration a to the left. So this is the observer's acceleration. And what is the observer reporting? This. So if I add the observer's acceleration to the relative acceleration it is reporting, see, relative acceleration added vectorially to the acceleration of the observer, that means capital A and small a, would give me what? Acceleration of the particle m in the ground frame. So in the ground frame, what would you see? In the ground frame, you would see a resultant of the relative acceleration of small m plus the acceleration of the inclined plane. Inclined plane reports this. Inclined plane reports this. So the reporting of the inclined plane plus whatever is happening to the inclined plane will give me a ground observer's framework. If this was a ground observer, then the ground observer would think that the resultant of the relative acceleration plus the acceleration of the observer, which is the inclined plane, A and capital A, this angle is theta, as you can see, this angle, this is A, this is capital A, this angle is theta, as you can see, would give me the acceleration of the particle m in the ground frame. In the inclined plane, small a. In the ground frame, resultant of small a and capital A, that's the story in the ground frame. Yes or no? Right? I'm going to build on this. Once you understand this clearly, small a henceforth is what? Acceleration of small m with respect to the inclined plane. Obviously, it's along the plane. And capital A is what? Acceleration of the plane. If I add these two, this is the observer and this is what the observer is reporting. The kinematic status of the observer and its reporting will together give me what? The absolute acceleration of the particle, that is the observed, right? I'm going to build around this. So I'm going to write equations of motion for small m. I'm going to write equations of motion for small m, keeping in mind that I know whatever forces acting on small m will produce a net effect, which is the resultant of small a and capital A. The net effect of small a and capital A would be the effect of all forces acting on small m. Now, whether I choose to resolve forces acting on small m perpendicular to the plane and parallel to the plane and write equations of motion of small m parallel to the plane and perpendicular to the plane, or I resolve forces vertically and horizontally and I look at the effect of these two in a horizontal sense and in a vertical sense, that does not matter. That is only cosmetic. But in principle, this is what I'm going to deal with. This being the effect in a ground frame perspective, small a and capital A put together is a net effect in the ground frame, and I'm going to look at forces acting on small m that will produce this effect. Cosmetically, I might do very many things, but in principle, this is what I'm going to deal with. Thank you so much. In my session that is to follow, I'm going to come down to downright equations in two mutually perpendicular directions. Aim at solving capital A, the acceleration of the inclined plane, and solving small a, which is the relative acceleration of small m with respect to capital M, that means the inclined plane. And then, of course, I could find the resultant of these two. That will give me the net acceleration in the ground frame. So that's my agenda for the session to follow very soon. Thank you so much. Bye.